Hello and welcome to this video. Sometimes when we're solving mechanics problems, we encounter situations where the forces don't quite point in convenient directions. They might point at certain angles to each other which aren't right angles. So effectively we can't put them on the axes that we would like to. So what we have to do is we have to resolve them into the directions that we're interested in, the two perpendicular x and y directions, before we can move forward. So what we're going to discuss here is situations where there are multiple forces acting, all right, which are coplanar. Now the word coplanar means they act in the same plane. So we're talking about a two-dimensional XY plane. And the forces can act at any angle within that plane. So we're also talking about situations where there are multiple, so three or more forces acting. And we have to resolve one or more of those onto the axes that we're interested in so that we can actually solve the problem. Now sometimes we're going to have constant velocity situations and sometimes the object is going to be accelerating, and you need to know how to deal with both of those. So here are some situations of what I mean by those. We've got a skier going down the hill where he has various forces on him. He has his weight, which is acting vertically downwards. And it's the weight, of course, that's accelerating him down the hill. But it's not all of the weight, because the acceleration is down the slope, whereas his weight is acting vertically downwards. So we need a way to figure out how much of that weight is acting down the slope and causing the actual acceleration. So that's what we're going to talk about. These situations are very similar. If we just take this one over here, we have the weight of the roller coaster pushing downwards. And just to add a little bit more detail, we would have the normal reaction force acting at right angles to the surface and presumably some sort of frictional force acting back up along the slope. Now the acceleration is going to be this way down the slope, so the net force is going to be somewhere in this direction. So what we're going to look at is how to find a way to do that. Okay, now I've done a little flowchart for you to help you through this process because it's quite a complex process. So the first thing you need to do is identify all the forces that are acting on the object. Now usually there are only 3 or 4, and we'll have a look at some examples of those. Then we need to choose a suitable set of coordinates, and we need to put the axes, the x and y directions, in suitable places. Now that's not necessarily going to be horizontal and vertical. It might be the actual axes might be more conveniently placed at an angle, and we'll have a look at one of those problems later on. Then the third thing to do once you've done that is resolve all those forces, the ones that aren't already on those x and y axes, onto the x and y axes by taking the x and y components of those particular forces. And then you have a look at your problem and decide whether the acceleration is 0, i.e. the object is moving at a constant velocity, or whether it's non-zero, i.e. the object is actually accelerating. Where the object is going at a constant velocity and the acceleration is 0, then we look at the x and y directions separately. The vector sum of the x forces, the forces in the x direction, is going to be 0, and the vector sum of the forces in the y direction is also going to be 0. So we use those facts and that knowledge to usually find out one of the missing forces, or decide whether it's going in a constant with a constant velocity or not. Where the acceleration is non-zero, i.e. the object is actually accelerating, once we've resolved all the forces onto the x and y axes, we can use the net force equals m times a in those directions where the forces are unbalanced and figure out our missing quantity, be that the acceleration or possibly the net force. Okay, so let's have a look at a couple of worked examples of those. Now, the first one I've chosen is an object that's moving with constant velocity because those are kind of the easiest to deal with. So here we've got a guy that's pulling an enormous weight, and the tension in the rope is the first force I'm going to identify, which is the T there. And then there's the weight of the mass here, and then there's some sort of frictional force, which we'll call F there. Okay, so those are the 3 forces we want to deal with. And so all we need to do now is to draw a free body force diagram for those and choose some axes and move forward from there. Okay, so let's just get rid of this guy for a minute and get rid of those forces because I've got a pre-drawn free body force diagram up here, which I'm going to bring out into there. There we go. Okay, and I've got a set of axes. So the first thing we do is put this diagram onto a set of axes, which I'm going to make slightly larger. Now, obviously, in this particular example, the easiest set of axes to choose is just vertical and horizontal. So we're going to choose the horizontal as the x direction and the vertical as the y direction. Okay, now this is the weight of the object, as we said, and this is the tension force here, and this is the friction force. And the question we're going to ask is, what is the frictional force acting on this mass? How much friction is acting on it when the guy is pulling with a force of 400 newtons at an angle theta, which is equal to 35 degrees. Okay, so the first thing we need to do is resolve this force T onto the x and y directions. Effectively, what I'm saying is we need to find Tx, which acts in that direction, and we need to find Ty, which acts in that direction. Okay, so that's Tx and that's Ty. Right, this is quite a straightforward calculation. So because we've got an angle of 35 degrees and effectively we've got a right angle triangle here, it's just the same as we were doing with vectors. We just use SOHCAHTOA to figure out what Tx and Ty are. So Tx is going to be, sorry, that's an equal sign, 400, and because we're looking at the adjacent side, we're looking at the cosine of the angle. Okay, so the x component of the tension is 400 times the cosine of 35, which, when you work that out with a calculator, is 328 newtons. Ty, which is the vertical component, is just simply 400 times the sine of the angle 35 degrees. And 400 sine 35 is 229 newtons. Okay, so we've got a force of 328 newtons acting in this direction. And because we know that the motion is with constant velocity, we can say that the horizontal forces will balance. Okay, they're in equilibrium and they'll cancel each other out. So we can also say that F will be equal to minus Tx, because it's acting in the opposite direction, but it's equal, effectively equal and opposite, which is therefore going to be equal to minus 328 newtons. All right, so the frictional force is 328 newtons in the opposite direction to the x component of the tension. All right, so that's the first problem we're going to look at. Here's another one. This time we're going to say that we've got this guy pushing his lawnmower across the lawn, and he's accelerating the lawnmower. Okay, so the lawnmower is going to be accelerating in the horizontal direction over here. Okay, so the forces that I'm going to identify on this one are the thrust force from the man pushing on a lovely Sunday morning, the weight of the lawnmower, and the frictional force acting back in this direction. There's also going to be a normal force in this direction, but we can ignore that one there. Okay, so those are the forces we're going to look at. All right, so again, I'm going to make this a little bit smaller because I've got a pre-made free body diagram over here. Okay. So let's just make this a bit bigger. So again, let's choose a convenient direction for our x and y. And again, horizontally and vertically will be the best one to choose here. Okay, actually, just for completeness, I am also going to put on the normal reaction force there. Okay. All right, so we're going to say that this guy is pushing with a force of 100 newtons at an angle of 40 degrees to the horizontal, but downwards in this direction. And the frictional force acting in the reverse direction is going to have a magnitude of 20 newtons. Okay, and the question is, at what rate is the, oops, that really doesn't look like a question mark. At what rate is the lawnmower accelerating? Okay, so we need to find the X and Y components of this 100 Newton force. All right, so we need to find this component here, which is going to be what I'm calling Tx, and this component here, which is going to be what I'm calling Ty. And again, from the rules of SOHCAHTOA, we just use the cosine and the sine. So Tx is going to be equal to 100 cos 40, because it's the adjacent side, and Ty is going to be 100 times the sine of the angle. Okay, so Ty equals 100 sine 40. All right. We also need to know the mass of the lawnmower. So we're going to say that the mass of the lawnmower is 80 kilograms. Okay. So now we know, actually let's just work this out. So the 100 cosine of 40 is equal to 76.6 newtons. We could work this one out too, but we don't actually need it because the vertical forces are going to be in equilibrium. So the force acting downwards is going to be equal to the force acting upwards because vertically there's no acceleration. But horizontally there is, so we need to work out what that acceleration is. So we know from our earlier work that the net force is equal to the mass, the mass times the acceleration. I'll just straighten that out a bit there. F net is equal to ma. Now we know what the mass is, and we can calculate the resultant force. So I'm going to rearrange this to A is equal to net force divided by mass. Okay, and the net force is just Tx minus F. All right, so we have 76.6, which is Tx, minus the 20 newtons for the frictional force divided by the mass of the lawnmower, which is 80 kilograms. Okay, which gives you an acceleration of 0.71 meters per second squared. Okay, so that's how we do one where we've got a non-zero force in one direction. So you take the force, you resolve it onto the x-axis, and then you use F equals ma to calculate the missing quantity. All right, now here's our skier again. And this time we're going to do something slightly different because we're going to choose our axes in a slightly different direction. Now this is an example in physics of a problem called the inclined plane, which is where an object is either stationary or moving at a constant speed or even accelerating on a plane that is not horizontal. Okay, so it's a bit of a classic problem. So we're going to identify the forces on the skier here, and again I've got a free body force diagram over here. Okay, there we go. So we've got three forces that we want to take into account. The first one is the skier's weight, down there, the normal reaction force from the ground, and the frictional force from the snow. Now the skier is going down a hill, and the angle to the horizontal of the hill is 30 degrees, let's say. The weight of the skier is, let's put it on this side, 800 newtons. So using G as 10, the skier's mass will be about 80 kilograms. So let's put that up here, mass equals 80 kilograms. Okay, which gives him a weight of 800 newtons. And we're also going to say that he is accelerating, whoop, lost my pen. He's accelerating at a rate of 2 meters per second squared. Okay, so this is mass, this is the acceleration, and what we're asking, or what we're being asked, is to find the frictional force. So how much friction is acting at this particular point when his acceleration is 2 meters per second squared, and his weight is 800 newtons, he's going down a hill at this angle. Okay, so the first thing again we need to do is put our axes on, but this time I'm going to switch the directions of the axes to make it much more convenient for me, because in this case we would have to resolve both of these forces onto the x and y axes. But if we tilt the axes so that they're in this direction, then these two forces sit on the axes already, and the only force that's not on the axis, on either axis, is the weight. So that makes our job much easier to try and tilt the axes. And so we have the x-axis, which is acting parallel to the plane, and we have the y-axis, which is acting perpendicular or at right angles to the plane. So the normal force is already along the y-axis, and the frictional force is already backwards along the x-axis. So the only thing now to do is to resolve the weight onto the x and y-axes. So that's what I'm going to do now. So we have an x component of the weight, which kind of looks like that. I'm going to call that wx. And then we have a y component of the weight, which I'm actually going to draw down here rather than along this axis, because it makes this triangle, oops, sorry, that's wy. It makes this triangle a bit more obvious. Okay, so wy. All right, now the only thing extra to do is figure out this angle here, which is the one we want. So if you imagine this is a larger triangle, all right, down here and down there, you've got a right angle in the corner. If this is 30 degrees, this angle here would be 60 degrees. So that angle there, which I'll call phi, is equal to 60 degrees. And therefore, because this is still the hypotenuse, your right angle is over here, wx is going to be 800 cos 60. So let's write that down. Wx is equal to 800, which is the hypotenuse, the actual vector itself, times cos 60 degrees. And likewise, wy is going to be 800 sine 60. Okay. 800 cos 60 is actually equal to 400, because cos 60 is equal to a half. And 800 sine 60 is equal to 693 newtons. Okay, so once we've got that, we can write down the equation that we're after. So F net is equal to ma. All right, but the net force is the sum of these two forces, okay, because the acceleration is down the slope in this direction. The net force is equal to the wx, the x component of the weight, and the force. So we can say that wx plus F is equal to ma. And now what we can do is plug in the numbers. So wx plus F is equal to the mass, which is 80 kilograms, multiplied by the acceleration, which is 2. So the net force is equal to 160 newtons effectively. So wx plus F is equal to 160. Oh no, that really doesn't look good. Is equal to 160 newtons. This is my little graphics tablet not behaving itself. Okay, so we know what Wx is because we've calculated it to be 400 newtons. So we actually just want to work out what F is. So we can rearrange this. So F is equal to 160 minus Wx, which is equal to 160 minus 400, which is equal to minus 240 newtons. Okay, so that's what the frictional force is, and that makes sense with this minus sign because we know that F is actually acting in the negative x direction. So we were expecting something to come out with a minus sign, and indeed we have. So the frictional force is minus 240 newtons. Okay, so just recapping then, just looking through this flowchart again, you identify all the forces, you choose suitable directions for your axes, and resolve all the forces onto the x and y axes, so you've got everything in pure x and pure y, including the components. And then for constant velocity problems, you just use the conditions for equilibrium, and for acceleration problems you use F net is equal to ma to find either the force or the acceleration that you don't know. That's it. Thank you very much.